Okay, so welcome back. In the previous videos, we've been having a look at the very beginning introductions to search. So we've talked about how to represent planning problems, types of task environments, things like this. I think what has kind of already started to appear though, right, is this idea that there is a difference between the abstraction of the search space that we are searching over, these ideas of the search tree, search nodes. We're just getting familiar with these concepts and we'll become more and more familiar with them as we go onwards. But we're starting to see, right, that is explicitly different than the state space. The state space being the original real-world problem, the places, positions you can be in, the states of being, and then you'll be taking actions in order to generate new states and so forth. So we're really seeing, right, there is this abstraction from the state space to the search space. In this video, we're going to delve deep into the nitty-gritty of what is different between these spaces, and also discuss the way that these two spaces grow at different rates. We're going to be seeing that most problems, even though they're defined in just terms of a polynomial state space, right here there are only 9 cells, 9 states you can be in. We'll see that the search space itself can grow exponentially. They are very, very different beings, and let's dive into why. So the first thing we should look at then, along this journey, is let's define what a state would be in this kind of world. So I'm going to be looking at the example of just a grid world. We're in a standard grid. This is one of the most common examples of pathfinding problems and search problems you'll see. So a state in this world is just going to be described probably in terms of x, y position. It's just going to be like a tuple. Hey, where am I? So let's draw then the equivalence of this based on the actual problem itself. So our initial state S would correspond to the state A3. Okay, so I think that makes a lot of intuitive sense. So I'm going to be drawing the state space, or discussing the state space over here. And then we're going to start drawing up what would be the search space. We're drawing up a search tree. So we begin at node S, that corresponds to the state A3. Okay, that makes sense. So before we move on there then, the goal state G, this would be defined then. What we're looking for is C1. Okay? Now, I'm going to look at essentially the size of the state space. We already talked about it. Number of states is extremely easy. In this case, there's 3, 3, 3. There are only 9 states. You can be in A1, A2, A3, B1, 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 B2, B3, so forth. The size of these problems, even if it's like a 10 by 10 grid, right, that's still countable. That's still very small, I think we would say. But we'll see that even in just a 3 by 3 grid, the search space will grow, I think. It grows exponentially, but I think it'll grow to a much larger extent than you're actually expecting. And so let's discuss why that is. So the main reason for that is, in this problem we're going to be considering just rectilinear movement. You can just move in the cardinal directions, north, south, east, and west. The reason why the search space is going to grow is because we are looking for a path, a way to get from the start to the goal. And the idea is that there are a lot of these. We can go all the way east, then all the way north. We could go all the way north, then all the way east. But there's everything in between. We could go east, then north, then east, then north, or east, north, northeast, so forth. There are many permutations, right, of the possible pathways that you can take between these two nodes. This is excluding silly things like stepping backwards along a path we've already come from. That is in a very naive sense, that is possible before we start to prune those things. So let's then talk about how these permutations of paths correspond to the search tree itself. So from the start node, there are essentially 4 things we can do, right? The branching factor here, there are 4 decisions. Do we move north, east, south, and west? That is what we describe as the maximum number of moves we can do. Depending on the rules of the world, these things may change, right? So here, hey, do we consider moving west to mean we stay in the same location? Or is it something that's not valid? There's a million different ways, you know. Do you tell your robot to do something and it stands put or whatnot? But in the very general sense, all of these problems we'll be answering later in future videos. For right now, we're keeping it extremely simple. There are 4 things we can do. We can spawn 4 nodes at level 1 of the search tree. At each of these points, right, once I've moved here, again, I have the same number of decisions. Each of these decisions spawn another 4 things we can do, and so forth, and so forth, and so forth. So very quickly we see that the number of moves required until we get to the goal, if we follow the correct path, is going to be 1, 2, 3, 4. We're progressing down this tree pretty far, and think about, like, I'm only drawing one of these node expansions at a time. I'm only following one version of this path. Now this is happening for all of them, right? All of these nodes, all of these decisions we can make, spawn another 4 things we can do. The branching factor is exploding. The search space is growing exponentially. So 1, 2, 3, 4. One of these is going to be our goal node G. When we find the goal node, we can stop. But hopefully what I'm convincing you of is that the search space, the search tree, is substantially larger than the 9 states we could have been. And so what is the key idea here? Why is the tree growing so large? It's because the order of moves matters. When you have any form of problem, that the decisions you make is sequential, right? It is a sequential decision-making process. These are very, very common problems in our everyday lives that we're making, and we can make intuitively and quickly as a human being. And in our search algorithms, we're also making these insanely quickly, mostly because the computational speed of computers is amazing. But you can really start to see actually the branching effect that your decisions can have. If I move east, it has changed the order of things that I can do, the new states and places that I can reach. So we're ignoring a lot of complexity here in this very simple example, but I think this is really an interesting topic, right? We're going to be seeing that the abstractions, the space we're searching over, can grow really large, and we're going to need to make very good decisions in how to actually deal with this, prune the space, traverse the space, and make meta decisions therein. So please join me for future videos when we start to explore search algorithms and ways that we can solve the problems we've laid out here. Thanks, and see you soon.